Is my mic okay?
Yeah.
Okay.
I can hear you. I mean, at least from like interpretable machine learning, right? But we had the same problem. We have the same problem in many other places. Well, looking at Amrit, we have a lot of that in neuroscience, right? We have no idea how the brain works, and we like it's sort of non-invasive. We're solving, in a sense, we're solving inverse problem, right? Well, sometimes we can model it forward. Geodesic, we cannot open up the planet. We just guessing, interpreting by building models and things like that. Then we have that's probably to the electrical engineers and us. Is someone's there? The what are they called? The delta functions, the impulse responses, and all of those systems. So we're kind of doing similar stuff, and then suddenly deep learning become this is very different. I don't know what's very different about those models. Why can't we use another system, reverse engineering of software and all of that kind of dark market of hacks and things like that. Also, like people have put a lot of thoughts. So can't we use all of that and interpret our models? Those are just my thoughts.
I have
basically all of the methods
actually,
we have. Sorry.
The main problem, I think, that interpretation or explanation is a vague term. So there is no ground truth that this explanation is correct or this explanation is wrong. And another thing is there can be diverse ways of explaining one single thing. So if you think that I am differentiating male from female, there can be diverse ways of distinguishing male from female. So and so on. I think that is the main problem, that there is no ground truth.
Well, actually, in your example, we can do just gene sequencing, right? We can find either there is Y chromosome or no. So at least on that level, we can tell the sex biologically.
Yeah.
There is ground truth in your example.
Yeah, based on gene sequence. But for example, I am doing image classification for male and female, or structural distinction. So how can I tell that I will be focusing on just these features to distinguish male and female? There can be several ways to distinguish them.
Yeah.
Actually, even if you look at the gene sequence, it's actually a very fuzzy thing, because there's a lot of XXYs, there's a lot of XYYs, and it's not as simple as it looks. And this is a whole like explosion, because yeah, what actually ends up being the phenotype and what they actually have is completely different, and it is very complex. So
yeah, I'm not talking about phenotype even. Yeah, I'm just talking about genotype, because you're getting your Y chromosome from the father side, right? Or
right. But like there are XXYs and they're female, so even though they have a Y chromosome, so yeah. But
how often does that?
One thing
how often does that happen?
More than you think. It's like an absurd amount. Like I'm sure like we have double X, like at least one of us is not fully a guy, or technically whatever you think it is. But yeah, no, it's a big percent. I don't know. I heard of like a Radiolab episode about it. Very interesting.
Klinefelter syndrome is an extra X chromosome, and it's 1 in 10 men have it.
1 in 10.
Yeah. Okay. So one of us. So there's 10 of us, right?
Yeah. Easily.
Well, I mean, it's provable that at least one of us.
Well, there are 16 people on the call,
man,
and we're all a mixture.
Boy, did I log in at the right time?
Wow. So on the explainable AI part, like the something that comes to mind for me is that, like, at least in the CNN, I'm guessing everybody knows this, but if there's like some people who are less machine learning people in here, then they might not. Like you can at least get some idea of what's going on with CNNs with like fast gradient sign methods on like the activation maps, so you can see what the filters are looking for.
Well, that's the paper today.
Okay. That's good.
Yeah. Okay. Well, I thought I didn't mean to derail the conversation into the biological sex discussion. But like just thinking about us having that other fields where those interpretability and explainability methods are important. And let's look at this paper
So
a little wider. Yeah. No. Go ahead.
that's absolutely true, but it's also true that the methods we use are very similar, if not basically the exact same as interpretability methods in other fields.
And I have also another concern about the interpretability methods we are using, because the thing we are actually focusing on, the relationship, the direct relationship of the prediction to the raw examples, to the concrete examples. But deep learning models usually learn from abstract representations that we are not dealing with our interpretability methods, because it is abstract, it is doing different levels of abstractions on the concrete samples, and then it is doing its predictions. But we are trying to map the deep learning model's predictions to the concrete examples. We are ignoring the intermediate abstract representations.
Yeah, one thing though to say in defense of deep learning is, and please jump in and tell me how I'm wrong in thinking this, because I'm just unaware if I am. But it seems like one of the things that you would lose if you enforced interpretability is backprop. It's like if you're learning a bunch of intermediate concepts that are like that are discovered through like backprop. I mean, it's going to be a massive task to make that explainable, and it is a massive task, but that's pretty much all I have to say.
Well, let's start the talk and see where we are at right now. This paper tried to be quite comprehensive in terms of touching the methods and the classes of approaches that are currently used for deep learning, at least for deep learning.
Yeah.
So
Okay.
you can share your slides.
Yeah.
We can.
Okay. So okay. So the paper title is Debugging Tests for Model Explanations. I forgot to mention the authors here, but I should have done it. Okay, so let's start with different explanation methods currently people generally use. So what is explanation? Explanation is basically giving some rationale of a model's predictions. So we can define a model with a function that maps from input space to another space of C dimensions. That means the number of classes. And for explanation, what we do is we give a sample to the model, and then it generates a class-specific logic. And we try to explain that what is responsible, what is special in the input sample that triggers the model to achieve that class-specific logic. So in general,
can I interrupt?
Yeah, of course.
Ideally, again, just abstracting from the math or like our task at hand. Ideally, what we want is to have a conversation partner that tell us, okay, this is blah, and then we can ask why this is blah, and then, well, look at this. This follows that pattern, and this follows that pattern, and so and so in this book was telling me that if there is this change, then it is blah. Or something like that, right? So ideally, we just want a conversation. We want an explanation pointing to some objective truth. It doesn't have to be pixels, by the way. It doesn't have to be on the image. It can be some prior thing, as long as it is explanation, right?
Yeah.
Because this image comes from the Google database, and all of the images that come from the Google database are PNGs. That's why it is a PNG. Like something like that. It doesn't have to be like connected.
Yeah, actually visual similarity or visual explanation is deceptive. So sometimes we think that, oh, okay, the heat map is looking very good. It is, for example, identifying the object very well. It seems like that. So the model is doing very good. It may be totally wrong. It may be working as an edge detector. It may be focusing on some specific pixels of the object, but it may not focus on the underlying structure of those samples. That means it may not focus on the distinguishing features of those samples. It may just highlight some pixels or some areas. So we maybe there is a possibility that we might be deceived if we believe in visual explanation.
Can you make like insert one because we're talking about the model and we're talking about explanation? It feels like what Mahfuz just said was about the model, but in fact what he said was about explanation method, not the model. The model may still have 100% accuracy in a test set. It may be very good, but your explanation method may still be edge detector.
Yeah, right.
So we're talking about two entities here, the model, which could be wrong, could be right, and the explanation method. Like there could be an explanation method that explains the model usefully, or there could be an explanation method that just gives us an edge detector for the same model.
Sergey, it's probably a stretch to make either claim. I mean, in the base level gradients, they are a part of the model. They're one piece of the model. So I don't think we can claim that, you know, oh, the model is an edge detector with 100% certainty, or that the detection method is an edge detector in 100% certainty. So I
don't agree with that.
These are intertwined.
So I don't think that the edge detection derived from some gradient method will be same as commonly used parameterless edge detector. But nonetheless, the interpretability methods can work as edge detector, very different from parameterless edge detector, but it's still there edge detector.
Well, but Noah is saying that the model is to blame. So if the model...
No. I'm saying you can't make either claim because they're too intertwined. We do know that even without these backwards or perturbation-based interpretability methods, we still find edge detecting filters in CNNs. Like we literally find horizontal or vertical edge detecting filters
because we need them.
Normally perceive them.
Yeah.
Yeah.
I mean, the model needs them to function. So the model has an objective criterion, evolutionary, whatever. It's the performance on the task. The interpretation method doesn't have that objective criterion. With interpretation method, we're just trying to answer the question, why did you make that prediction, right?
Yeah, we are trying to interpret the model. The interpretability method is actually trying to explain the model. This is its task, yeah. So broadly, the explanation methods fall under two categories. One is called gradient-based methods, that we commonly refer to as saliency maps. And another one is called perturbation-based approaches. So while I was discussing with these ideas with Sergey a few days back, so he was actually not very convinced because he was saying, oh, okay, so in saliency map, we are also doing perturbation. So what is the difference between these two perturbations? So there is a big difference between these two perturbations because in saliency map, we are doing gradients. And while doing gradients, we actually nudge the input. We slightly prod the input value. But in perturbation-based approaches, we either omit the features or use the features. just binary perturbation. So do you have any question?
Well, let me know when I can say something in my defense.
Yeah.
I have a question.
Okay. So
I don't know if this falls under perturbation-based approaches, but I read that they're also using neuroscience techniques on artificial neural networks to measure the neurons and to see what signals they're picking up on. I don't know if that falls under interpretability methods, because I don't think it's like it may not be sort of far ahead enough to actually explain things, but I wonder if it's something.
So actually, sensitivity methods actually, or saliency maps actually focuses on the effect of output score with a small change in input. And perturbation-based approaches actually focuses on contributions of each input dimensions on the output score. So the contribution means how much that input dimension is contributing to the value of the output score. That means the marginal effect, not the rate of change. With respect to, that means the contribution of the input dimension when it is present with respect to when it is absent. That means what will happen if it is present with respect to what will not happen when it is not there.
Yeah, I think you should go ahead. Otherwise, we will never gonna get through your slides, because I do have a lot to say. But yeah, let's hold it.
Okay. Okay, so these perturbation-based approaches are usually called feature importance. Sometimes we get confused that maybe saliency map is giving feature importance, but in literature, the perturbation-based approaches attributions are called feature importance, and gradient-based approaches are called saliency maps. And there are lots of other methods, for example, rule-based approaches that is basically used for structured data like tabular data, but not for unstructured data like images. Okay, so the gradient is actually the gradient of output score, or the logit, class-specific logit with respect to the input sample. And another method is called integrated gradient. Though it is based on gradients, it is called attribution methods because it computes basically the marginal effect of each input dimension to the output score using gradients. So what it does is it takes lots of interpolated values between baseline and the input, and then sums them up to calculate the marginal effect of that input. Any question?
What is baseline?
A baseline means some value that means almost nothing for the model. For example, in case of image, it can be 0. That means in baseline can be a black image.
If I may, a lot of the research that uses or focuses on integrated gradients, they use a black image. In fact, some of the implemented libraries online that you'll find, the default is just a black image or just zeroed out space.
So it actually takes different interpolation points between black image or baseline to the actual value, and then computes gradients and takes the weighted average of all those gradients to compute the marginal effect of the actual input to the output score.
On a linear path?
On a linear path, right?
Okay, just a linear path.
Yeah. But unlike gradient methods, which is usually called sensitivity methods, integrated gradients is called actually the salience method. That means it is called the feature importance. It is calculating its marginal effect on the output score, not just the rate of change. Okay, so there are also some ensemble methods that can be used on top of the Bayes estimators. So by Bayes estimators, I mean the gradients and integrated gradients. So on top of these two methods, we can use different ensemble methods. So it is basically a noisy version of the Bayes estimators, but it will take different estimates of the Bayes estimations and will take the average. For example, in smooth grade, we can add some Gaussian noise to the input and then take gradients with respect to these noisy input, and then finally average, take the average to calculate smooth grade. So smooth grade squared is similar to smooth grade, but it will just take the square value of the of each estimations. And variance grade is actually the same idea. That means first of all, we need to add some noise to the input, then take the gradients. It will be considered as one estimation. We'll be taking multiple estimations, then we'll take the variance of all of these estimations. That is the var grade.
Why would you use one of these over the other? Because they sound pretty similar.
It sounds similar. So I think smooth grade squared is actually trying to ignore the sign of the estimations. But I am not sure about vargrad. But if we use smooth grad, that means we are focusing on signs. That means some estimations can be positive, some estimations can be negative. And if we use a smooth grad squared, that means we are focusing on numerical values of the importance, not their magnitude. Not
Well,
their
we're sort of favoring higher magnitudes.
Yeah. In smooth grad squared, yes. But I'm not sure about vargrad. So Sergey, do you have any intuition why we are using vargrad?
Well, we're looking at, well, variance of the gradient, right? The most unstable places, I guess, where noise effects are largest, like they throw things back and forth. So I guess it is like sensitivity to the noise. If we add the noise, the changes are most dramatic. But I would take the variance with respect to the output, but this one is taking the variance of the gradient. So it's hard.
Yeah. Okay, so there are some other methods usually called signal methods. So it is also based on saliency maps. That means the gradients, but while doing back propagation, it actually modifies the regular back propagation process. So by modifying regular back propagation processes, several methods have been proposed in the literature. So we will see that these methods have some pitfalls in debugging models. We'll see in the results from this paper. Okay, so there are two very commonly used perturbation based approaches. One of them is called LIME and another one is called SHAP. So I was very interested in LIME because the idea of explanation is very interesting, because what they used is creating another model to interpret the original model. And the new model is able to give faithful explanation, but that will be faithful in terms of locality, but in global terms, it may or may not be faithful. For example, what it does is it takes a sample X. Okay, it takes a sample X and its interpretable version X prime. So interpretable version X is the raw sample, and X prime is actually interpretable version. That means the different patches of the input. So we can mark different patches. For example, if our input is an image, so we can identify different areas of that image. For example, we will be focusing on this portion, we will not be focusing on this part, sometimes something like that. So our focus patches will be marked as 1, and the parts we want to ignore will be marked as zeros. So we are referring to this version of input binary vector is as interpretable version of the original sample X. Now what they will do is
I'm sorry, could I ask a quick question?
yeah,
Um,
sure.
Is that the same thing as attention? So do you like learn it, or it's just like a mask? Or not?
Yeah, for example, you can identify, for example, while image recognition task, maybe you can identify different patches of the image that you want to focus on. For example, the middle portion of the image, and the peripheral portion of the image you can mark with 0. The area you want to focus you can mark with 1, something like that.
So it is kind of like saliency map basically behaves like a mask for attention.
So we are not talking about saliency maps right now. We are using different method for explanation that is called perturbation based approaches. We are not using gradients now.
This also is not, I don't think, comparable to attention, because it's not really a learned weight.
Yeah, so you put a mask. What does sample around the mask means?
Okay, sample around mask means the mask is collection of ones and zeros. So what they will do is they will collect only ones, not zeros. 1 means the
Inside mask. So basically sample inside the mask, whatever passes through.
Right.
Don't take the the masked out values.
yes, they will take only samples from ones, and then they will map it to the original sample from the binary vector, and then they will compute the classification label of the original model. So that is called f of zi. That means first of all they will take they will sample from the interpretable version, and their sample is zi prime. So based on zi prime they will
Is it
map.
a pixel value? What is that? Like, imagine X is an image. We mask that image. What is Zi prime with respect to that image?
Okay, so first of all we need to understand what is x prime. X prime is the interpretable version of X. That means ones and zeros over the actual samples. X prime. So from the X prime they are taking samples, and that sample is zi prime.
So I think one of the examples is that's useful is for text. So you'll have a line of text, and your Z prime will be changes in the words. Instead of the cat is in the house, it'll be the cat chair house or whatever.
Yeah, in case of text, yes.
Oh, okay. So
because conceptually, the idea is you want to keep this as interpretable as possible. That's why LIME exists, is because you want, all these other interpretability methods can be messy and they look noisy to us or whatever, but if you can keep your perturbations and your inputs interpretable to a human being, you can better wrangle and understand the results.
Yeah, so it takes samples around X prime, then maps these sample to the actual samples GI. And for these actual sample, they compute the prediction score. So based on this prediction score, the newly sampled interpretable version and the distance of this new sample to the actual sample, they take several samples of these and compute a database Z. And on this data set Z, they build a linear or very interpretable model, and then finally interpret the actual sample X. Question?
Yeah, what does lasso do there? Like, what are you solving with this?
They are trying to solve an optimization problem. And solving that optimization problem, they are actually trying to build some linear model based on these predictions, the interpretable version of the samples, and the weights. Weights means the distance of the new samples with respect to the actual samples. So based on this data set, they are trying to build a linear model using K-lasso.
The motivation for lasso is just to make it zeros or ones, basically, to make it as interpretable as possible.
So they take this set Z and they fit a linear model.
Yeah, right.
Sparse linear model. I mean, that's
Yeah, for this sparse.
okay. And so whatever the coefficients W are remaining, that will be our new mask or something like that.
That will be the interpretation. Yeah.
Okay.
As to what was important for it. And then they don't learn the segments. They use like a image segmentation model off of SK image.
We do a simple example, like, for example, instance X is a table, and we have apple on the table. Interpretable version is a mask of an apple. And, for example, classify as convolutional neural network. What will be similarity?
So what is K in lasso? Isn't it kernel? I don't know what they're trying to do. Sorry.
Actually, maybe it is the sparsity they are expecting.
Oh, K sparse. Okay, so it's a hyperparameter.
Yeah, it is the parameter length of the explanation.
Okay. Thank you. Thanks, everyone.
And another perturbation based approach is called SHAP. It is actually based on Shapley values. So if for computing SHAP, different random permutation of the features is used. So for one permutation, it starts with a baseline. That means, for example, the black image. In case of image classification task, it can start with a black image. Then based on that permutation, it will add one dimension at a time and will compute the marginal effect to the output score. And then it will repeat the similar process. That means lots of permutations, and then all of the marginal effects per input dimension will be averaged to compute the actual marginal effect of each input dimension.
We may need a deeper dive next time, and I know Noah already spoke about it a year ago or so, but let's move on, I guess.
So I think you have a question, so you can quickly ask me. I think it is possible to answer right now.
No, my question is more about aren't we like, why is it not the same as especially this one, the same as our sensitivity analysis? So when we are in sensitivity analysis, we build a tangent space to a specific point, which is our image. When we're doing this, we're moving to the origin, everything is zero, and choosing a random subspace So instead of being at x, imagine our x is 0.22. We are, let's check 20 and let's check 0.2, but we're still checking the tangent space, basically. We're still looking at sensitivity. It's just with respect to random points.
So I have one question. So do you think that if we take gradients of output score with respect to input, and then some of the gradients will be equal to the output value? Do you think so? Sorry, I cannot hear.
I'm saying, yeah, like the gradients are independent. Like if you said 0, and unmask something versus you said everything, the specific first order gradients will not change much, right? The specific dy by dx, they will be, you didn't change them.
But my question is, if we take gradients of all input dimensions, do you think that sum of gradients of all input dimensions will be equal to the output score? It will not be. It will not be. So if we take gradients of input dimension, gradients of output with respect to all input dimensions, and each input dimension, and then sum them up.
Why do we sum anything up? We know the gradients for each.
Yeah.
They're independent in a sense. They are dimensions.
Yes, but in this case,
by the way, yeah, we can look at the Hessian for that. But
yeah, I what I'm saying is, in this case, in the shape case, it will not be independent, because each input dimension's marginal effect will be calculated. So ideally, the sum of all importances will be equal to the output score, ideally, or very close to the output score.
Yeah, so geometrical interpretation.
Sergey, sorry, Sergey, I agree with you. So you're welcome for that. But I think what's important to note is that Sergey, you're right. If you calculate just the baseline perturbation versus these gradient-based methods, they're gradients. The values are the same. They're just gradients. I mean, sometimes you get differences because saliency is of the correct class. You'll get differences, and you'll actually get more differences in the negatives versus positives. But these differences are subtle. They're not measured. It's, it's not like people, they use the Newtonian method to calculate gradients. It's not like once we got autograd or backwards that we just threw out Newtonian methods.
Yeah, exactly. It feels like they use the finite differences instead, and they use finite differences on random subset. But even ignoring that, what I'm struggling with is, I think those methods are not different. They're connected. I'm struggling with geometric interpretation. We have a ball. We have a point on the ball. Well, we have a point on the surface, and we have a corresponding point on that ball. And we have a tangent space here. That's what we're doing with sensitivity. What this does is like, oh, instead, let's look at this parabola, the cross section. Well, did anything change? Not really. But if you start summing the gradient in random subsets of dimensions, yeah, there you're doing something ad hoc and funky. That then I can't comment. But still, I can get the same from my single pass of backprop and looking at the subsets of what I get. Okay, anyways, I think I'm derailing the conversation. Let's move on.
Okay, so let's focus on their task. So what they are trying to do, they are trying to investigate that the explanation methods that are being currently used are effective for identifying bugs in the model. So they have classified bugs in different categories. For example, the bugs can be generated from the training data, and the bugs can be generated from the actual models, or the bugs can happen at the time of test. So during training data, there can be bugs in the labeling. That means the wrong labels may be assigned, or there might be some thing in the training data that may introduce spurious correlation with the classification label. And for example, in spurious correlation example, for example, we are classifying bird and dog, and all birds are placed in the sky with a sky background. And for example, all dogs have been placed in some forest background. So it may happen that models are identifying the sky instead of birds, or it can happen that the model is identifying the forest instead of dog. So there can be some thing like this kind of spurious correlation between training samples and the classification levels. And another thing may happen that
I can comment about yours and Noah's experience again, the firsthand. If we only have two classes, like in most of their examples, if for those of you who read the paper, are very contrived, because if we only have two classes, all we need to do is to look around. That's why you get here, and to see if there is a cat there, and even never bother about the second class.
Yeah, right. You're right. Yeah.
If the cat is not there, everything is highlighted. I looked everywhere and I didn't find a cat. I don't need to know anything about the second class to be able to do perfectly.
Yeah.
I think a lot of that is made ridiculously easier though by the fact that we have multiple frames. Most of the frame that's not changing doesn't matter. And the part of the frame that's changing matters.
And in test case, what may happen is that the test data is coming from out of domain examples. For example, the model may be trained on disease data set, MNIST disease data set, and the test sample may come from, for example, fashion MNIST data set or something like that. Or maybe the model has been trained on dog versus cat classification, but the test sample is from human being sample. It may happen. So what their contribution is that they have categorized different kinds of bugs that may happen during training, model, or test. And they have actually investigated some insights that they have derived some insights that feature attributions methods we are using right now can identify the spurious background bug, but it cannot conclude about mislabeled or normal training examples. And another thing they have discovered that modified backpropagation methods we have mentioned earlier are invariant to higher layers. For example, if we reinitialize the top layers, the attributions will not change. And attributions for out of distribution examples are visually similar. We'll see in the result section. And they have also investigated with human subject study about the attributions and the predictions from the models. Okay, we already talked about these. So they used a data set. They are doing actually birds versus dogs classification, and collected dog from one data set and collected birds from another data set. And they have used a CNN with 5 convolution layers and 3 fully connected layers. And their model achieved 94% accuracy on the data set. So for spurious bug implementation, what they did is they placed their dogs onto a bamboo forest background, and they place all of the birds on a sky background, and then trained the model and achieved 97% accuracy. But the problem is that they tested their model on a sky versus bamboo forest test set, that means there is no dog and there is no bird, but they achieve 97% accuracy. But they trained the model with dog versus cat data set, but tested the model with just sky versus bamboo forest and achieved 97% accuracy.
What is accuracy in this case? A sky versus bamboo.
Yeah,
Okay.
sky versus bamboo, but they trained the model on birds versus dogs. Bird versus dogs, but dogs placed on top of bamboo forest and birds placed on sky background, and then trained the model. But during test, there is no dog, there is no bird, only skies and bamboo forest.
Yeah, so shortcut learning.
Yeah, right.
But they, why is it significant? They created that situation, right? How does the model know, is it dogs or birds, if always on the dog background, there is bamboo forest? And like the model is trained to distinguish those two classes, and sky versus bamboo forest is predicted. So why not sky versus bamboo forest? Because of the consistency. They didn't do data augmentation properly, or
Actually, what they intended to do, I think, is that there might happen that the things we want our models to focus, the models might focus different things, if it is possible. For example, there was a chance for the model to look into the skies and the bamboo forest instead of dogs and birds, and the model did that. Okay, so this is the result for spurious bug implementation. So this is the spurious image, and this is the only background. So there is a lots of similarities if it is only background, and if the dog is placed on the background, there is lots of similarities between these two.
interestingly, not a single method is promising in this task.
Yeah, right.
So, shortcut learning, like the models just.
Sorry. Do you know what the scale of these images are? Are they 0 to 1, or do they include negatives?
I didn't understand. So you are saying 0 to 1 means what?
Well, actually, are they only positive values?
Maps? You are talking about the heat maps. So they didn't mention that whether
They
it
did
has
not.
been scaled or not. Yeah.
Which is and I think you've had this experience. When you look at just the positives and negatives, you get different values if you take the changes of the correct class versus the changes of the incorrect class. So by using only absolute or positive values, it makes the results problematic. If that's what they're doing, I don't know.
Yeah, I didn't check
Wait.
their results, and they didn't mention it in the paper.
Wait a second. So like if you take a look at lime and like shape and whatever, it doesn't show that you're paying attention to the dog or the cat per se. Like the future map doesn't include them. What happened though is that the participants didn't care about the future maps and cared about the participants. That's why I hate this paper, because it's not about debugging it, but it's about trust in models, predictions, and attributions or saliency maps, etc. It's not about like actually debugging things.
Isn't that the point though? Partly of interpretability, because interpretability is about us and us being able to understand the model. And if we can't understand the results of the model, if we make a subjective decision about it, that's what matters.
I mean, like if you look at lime, for instance, you could say that there's no dog in there, but
Yeah.
you're giving it to 54 people in an IRB study who probably don't know what Lime is.
Mhm.
And so, like, I don't think that they would trust Lime because they don't know what it is and they don't know why it would be useful to them.
Yeah,
So
human
then-
study,
then-
they have also conducted human study. Human study says that the people are generally not very convinced with the attributions the explanation methods usually give. So they actually rely on predictions.
Yeah.
When
and,
a
like,
model
it's
does
not like,
good predictions, they rely on the model and usually recommend the model for practical uses. But
Yeah.
they actually don't believe on attributions.
yeah, and
we-
so that's about trust in the attribution model and less of like how good the attribution models are.
Mhm.
Well, they include other results. So
Yeah.
it's not like this myopic thing of we only want human beings' input.
Yeah.
I think it's reverse, Kevin. That they trust how good the models are. They don't care about the attribution.
Yeah.
Yeah, they don't care about the attribution at all, even though the attribution is technically correct.
Mhm. Okay, so let's focus on the human study. So while doing the human study, the end users were given the original image and the model predictions and the attribution maps, the three things. And their task is to work as a quality insurance tester. For example, whether they will recommend the model for practical use or not. So if the score is 5, that means they will definitely do it. If the score is 1, that means they will definitely don't do it. And they are also asked to give a rationale for their score. So if they say definitely, why they are saying definitely, and if they say no, then why they are not recommending, something like that. So this is the result for different experiments done in this paper. For example, for normal model, this is the result for normal models, and this is the result for out distributions. That means the test samples are taken from different domain, and this is the result for the models trained with clipped or some wrong labels, and this is the result. The fourth one, this is the result of training a model with some spurious backgrounds training data, and this is the result of human study for the models whose top layers have been reinitialized with with some random weights. So, and the right hand side figure shows the participants' motivation for their decisions. So as we can see for the normal model, that means there is no wrong label or spurious correlation in the training examples. Most of the most of the end users actually recommended the model for practical uses. And why they recommended? Because they said that the attributions the models are giving are expected, mostly expected. And for example, for spurious bugs, they rejected the model because they think that they are not giving the right predictions. Basically, they have relied on predictions. They have given less values to the attributions.
Isn't it like slightly a different story? That when the model is correct, they're looking at attributions, but when the model is incorrect, attributions don't matter.
Yeah, something like that, right? So first of all, they focused on predictions. If the prediction is correct, then maybe they are interested to look at the attributions. But if the prediction is wrong, then they totally ignore the attributions.
Well, but it's kind of a common wisdom, right? Don't try people who lie to you. Don't try to interpret them.
Yeah, right.
Well, but we know that actually in the paper, in the medical imaging paper that you read, and Anis is not here, but we've seen a lot of papers submitted with Anis in our journey last year, submitted to high impact, and even some published in high impact journals, where people analyze models and compare models that predict like at 55% accuracy or like very close to noise. And like the point here as well is that you don't even get into the analyzing business if the model is not doing well, because it's just, yeah.
So for the flipped example, if the input, some of the training examples are mislabeled, then as we can see that their attributions are not very changed. That means they're quite similar. So end users reject these models mostly based on classification levels, because their classification accuracy drops when some training examples labels are changed. The classification performance drops, and the end users actually reject these models for recommendation because of performance drop, not for the attributions, because the attributions are quite similar.
But I have a question. Is it the same model? Like if you take a column, is it the same model?
So no, they are different. For example, correct label means
I'm talking about the model, not the interpretability methods are all there, but is it the same model? You change the label with respect to which you compute the interpretability. But I wonder if it is the same model.
no, it is not the same model.
So I take the grad, right? The first column, and
Yeah.
I have 4 pictures. For each of the 4 pictures, it's a differently trained model.
They are comparing a model trained with correct labels against the model trained with some wrong labels. That means 2 models, one trained with correct labels and another trained with some wrong labels.
I'm just trying to decipher this in terms of this degrees of freedom. If the model is just learned to find dogs, then it can predict.
Yeah.
Even like I don't know, but we're almost out of time. Yeah. Anyways.
Yeah, it can happen. But they have found lots of similarities between these 2 attributions found from 2 different models. The structural similarity is almost 75% to 99%. Yeah. And
Sergey, to answer your question, it actually says in the abstract that it's mislabeled training examples.
Well,
So
from
they're
Alex's
different
work on MeshNet, we know that mislabeled training examples, especially when they're random, don't matter. The model learns to generalize over them.
but I think if the number of classes is high, for example 4, 5, 6, it may not happen. As you said, that they may use different degrees of freedom for binary classification task. They may just learn only one thing and they are just fine to identify the other thing, right?
That's one way you insert Trojans into neural networks, actually.
Yeah, but if the number of classes is, for example, 5, I think it may not happen if we flip the labels.
I think in one of the paper that was like related to SNP, they actually did a random label fitted experiment, and they actually learned to generalize even for like totally random labels if the model was like large, and that was for like 10 classes, even 100 classes, I think.
And
Like Cypher 10 and etc.
Let me make an announcement because we're done for the time. Like people who want to stay and discuss, let's continue discussion. But if you have to disconnect, because I know people schedule meetings back to back with Zoom, it's very easy. You just feel free to disconnect. But random, okay, just coming to your comment, Riyasat, random labeling. Yes, the model can learn any random label, right? That is our main problem here, that we have. First, we've built a universal function approximator, and then we're asking the question, oh, what is that function that it approximates right now? So it's kind of, yeah, it can approximate any function.
Yeah.
So
generalize. What does it mean to
generalize? Oh, maybe it will not generalize. I mean, after it learns, yeah.
And the performance drops. Even the training accuracy drops. If you randomize labels from the ground truth, even the training accuracy will drop. So Riyasat, I have a question. So what are the attributions in that case? If the labels are randomized and the model learned from those randomized labels, what are the attributions in that case? The attributions are quite similar to the ground truth.
What do you mean by attributions? Like
attributions means the saliency maps.
I don't know about, like, the experiments were not about saliency maps, so I just read the paper, and I don't think they like went into saliency maps and other like those kinds of details. But the basic premise of their experiments was that whether they could learn like randomly shuffled labels, and whether like the model, it was like a test for generalization. So they were like going for the case that the training accuracy like will go down even the labels are randomly shuffled, but the model will not generalize. So you can use it like a test, some sort of test for like
some kind of sanity
test for like sanity check for generalization. I can link the paper.
Yeah. And this is the result for model debugging. That means model contamination debugging. So what they did is they randomly initialized from the top layers, and they have observed that some explanation methods that are quite based on modified backpropagation actually very invariant to the top layers. For example, if we look at guided backprop, or if we look at LRP SPEP or LRP SPBF pattern net, we see that even if we randomly initialize the top layers, the attributions or the saliency map don't get changed. They remain quite similar.
I think it's like the pictures where you were pointing out hard to interpret. The rank correlation or SSIM are easier. The faster it goes, the better, the more truthful is the model. That it's kind of like, okay, the model stops performing, the interpretation drops. It's more what humans expect, right? And if you notice, the gradient-based method are best in there. They're like, oh, the model is noisy, we're not reporting anything good, like which we want. So that's an interesting behavior. If you look at square grad, if you look at just the gradient or vgrad, whatever that stands for, as soon as you start perturbing, the interpretation is blur. So it's only giving you whatever model actually can perform. Because when you perturbing the noise, well, and again, it's all subjective, right? Because it depends on what you want as a scientist. Maybe you have a degaussed hard drive and you still like want to decompose or restore some parts. So like you have a damaged model and you want to restore that something because you don't want to retrain the model. But if you really want to use the model as is, then the gradient methods are telling you the model is broken. They're like immediately telling you the model is broken. Something happened to the model. it's like a parity check in a sense. Like, oh, look, saliency map is blurred. That means top layer or any kind of layers are affected. That's my interpretation, at least. I was staring at this. That's why I included this figure in my advertisement of the talk, because I was like, I spent quite some time on this figure trying to understand.
I feel like what you said is pretty important. It's something I was thinking about yesterday, but I probably need to rewatch this recording to figure out what you're trying to say.
Okay, so this is probably the last result from their paper.
Yeah, we have to stop at some point.
Yeah, this is the last paper, last result, I think. So the result is, this is the investigation of checking out of domain samples cases. For example, for the first one, fashion MNIST model, that means this model has been trained on fashion MNIST and the test sample is from fashion MNIST. Okay, and the second one is MNIST model. That means this model has been trained on MNIST dataset, but now is being tested with samples from fashion MNIST. And this model, the third model, actually, it was trained on birds versus dogs dataset. Now is being tested from samples of fashion MNIST dataset. And the fourth model, it was trained on ImageNet. So as we see that whatever the training data set was, irrespective of that, the attributions for out of domain samples is quite similar. So explanation methods, it seems that explanation methods don't have the ability to identify a test sample if it is from out of domain or from in domain.
Oops. At least not in the way we expected. And just a joke, or sort of, when I was reading this, analyzing this, I was wondering, why did they put a beaker among this 4 data sets or 4 models? And only now I realize it must be a dress. But okay. but the thing is, I don't know why. Thanks, Eloy. I don't know. I couldn't understand what the picture is and how did they come up with it. Why that picture, not any other? And but at the same time, when you're an expert in something, like we scan our gaze, the scanning of this the scenery doesn't change. So the good thing about what we're seeing at this figure is those models are good object detectors. You can have a bad story or a good story. All of those models, even though they see the dress for the first time, the models, not the interpretability methods, they are detecting the object. There is something and they see it, but it's not their class. I don't know what they're predicting it. So I mean, is it bad or good? What would you expect, or what would we expect the models to show? A blur? But there is something on the picture, right? What did we expect?
So if a model, if an explanation method gives something like object detector, that means if a model just performs as an object detector, then it may not be able to explain that model, right? We may not be able to explain that model using these heat maps or saliency maps. If a model is always an object detector, then how can I explain them visually?
How can I explain them visually?
Yeah, for example, as you have mentioned that whatever the model was trained on, the model is always performing as object detector, right? So if it is object detector, then there is no way to visually explain the model.
Okay, I see what you're saying.
Mm-hmm. So there is no meaning to take saliency map out of that model as an explanation, because as you have mentioned or indicated that saliency map will always refer to the object being tested.
Okay. So, do you have any concluding remarks or concluding questions? Because we went way over time and other meetings are upcoming. So, everyone.
Just thanks, Mahfuz.
Yeah.
Yeah, thanks, Mahfuz.
Yeah, thank you.
Nice.
Thank you, Mahfuz.
Thank you, everyone.
Everyone. See you next time. Alex will be talking about advances in transformer development, and everyone. Bring your own your favorite Bumblebee or Optimus Prime or something.
Wait, aren't transformers now being outperformed by CNNs again? We should probably switch up the topic back to fish's net.
No, I'll bring my linear model and we'll outperform everyone.
Your K-near's neighbor model.
Oh, well, sorry, we're still over time. Actually, I did manage to go through Pedro Domingos's paper. It is fantastic claim. I have one thing to resolve. I don't understand how one thing. It's on neural tangent kernels plus the path kernels that he introduces. And finally, my intuition is kind of confirmed, but sort of confirmed, because I don't trust everything what he said. It is a kernel machine, so it is a KNN. But it's an efficient KNN. It is not a quadratic KNN where we have to look through all of the pairwise distances. So it looks like that's what it's doing. Not just transformer, everything. Anything that you train with SGD. Even if you use a linear model and train it with SGD, and Brad is there. Brad, remember when we wrote down what the model is? The random model plus the sum of all of the gradients. So he took advantage of that and to show that it's actually kernel. So it's fun paper. We should talk about it sometime in May.
Yeah, I should really appreciate. Really appreciate if someone like talked about neural tangent kernels. Like
Can you send that paper?
Integrate. Yeah.
After this, yeah, but it is Canon all the way. Yeah, sorry, not really. There are lots of questions about his claim.
So we should start using evolutionary algorithms again.
That's actually what Pedro is claiming, but he's very levered in that case. Not evolutionary algorithms, but we should not be tribal, because the solution will not come from one single thing. We should explore, keep exploring. Like that.
So,
well,
Sergey,
thank you very much.